Let's look at some more applications of integrals. First, we'll look at some pressure force, and then we'll look at a probability one. Here's an important idea. When you look at a dam or anything that's holding back water, a tank plate, it could be a fish tank, the pressure at any point on the dam tank plate depends only on how far below the surface the point lies, and not on how much water the dam is holding back. All right, for example, if we look at fluid pressure, P, the force per unit area at depth H is P equals W times H, where W is the weight density, i.e. the weight divided by volume. So the units of this are going to be pounds per cubic foot, right? The weight divided by the volume, times the depth, which would be feet, and we get pound per square foot, and that should agree here, force per unit area. All right, to find that total force, the first thing we're going to do, as always, is we're going to look at one slice. So we're going to say we have our fluid pressure times our area, and then that's one slice, and we'll sum them up. Then what? We let the norm go to 0. Remember, the norm's the thickness of the largest subinterval. We have the sum, and that is the force over area times the area. And as that norm goes to 0, we're going to get the exact value. And we'll go from C to D, since these are Y numbers, of force over area times area. All right, let's take a look and see if we can apply this to this problem here. The vertical end of a tank containing water is weighing 62.5 pounds per cubic foot, has the shape shown. That's half an ellipse. Find the force acting on that wall. First of all, this idea should be somewhat familiar. We looked at population density before, and we had strips of area, and we found the area times the density. We found the population for that strip. We summed them all up. We're going to do a similar thing here. We'll say, here's our strip. This will be delta y. We're going to need to have an xy axis. We'll put it here. And so this bottom point will be at -8, and the top will be at 0. And the value going down will be the -y, because we want to keep our things positive. All right, we need to find what's the area of this strip. Well, the area will be the length of the rectangle. That should be pretty easy. Same thing as we've been doing, times the thickness, right? And so the length of that would be the right side minus the left side, this x value minus that x value, or we could just say the x value times 2 by symmetry, and then delta y. And since this is in terms of y, our delta y is going to become dy. Let's go ahead and write the equation of this ellipse. That'll be x squared over 5 squared plus y squared over 8 squared equals 1. Let's solve for x squared. So we'll have 1 minus y squared over 8 squared, and then we'll multiply everything by 5 squared. Make sure we have our parentheses. Let's go ahead and get a common denominator of 8 squared, and we'll pull the 8 squared part out. So we'll have 8 squared minus y squared equals x squared. Now we'll go square root. We have our plus or minus, and we get our 8 equals 5/8 times the square root of 64 minus y squared. So since I'm only just going to do double the y value, that's why I'm taking the positives there. All right, when we come over to this, we're going to say what? We're going to sum it all up, and in general, you don't have to, just like we did for volume, we started off writing everything, and then we can skip over that once we get it down. But I'm going to put the units right now. So we're going to sum up 62.5 pounds per cubic foot times our depth, which will be our negative y, feet, times our area, which will be 2 times 5/8, that's what we have over here, square root of 64 minus y squared, and then our delta y. We let our norm go to 0, we're going to get our integral from this, and now we can find our force. And I'll show you a couple ways. For right now, I'm just going to pull out that 62.5, and we have 2 times 5/8 will give us 5 force. We're summing up from -8 to 0 of, leave a little space here. In fact, I'm going to have to squeeze in, leave a little space there. We'll have negative y times the square root of 64 minus y squared, and the delta y becomes dy. So we now need to integrate this. We see 64 minus y squared is in the square root. Instead of doing a substitution, you could do that, but for right now, let's just go ahead and write it. The derivative of the inside is just negative 2y. I have the negative y, so I'm going to put the 2 there, and I'll put a 1/2 on the outside. So now that negative 2y will get sucked back in when we go the antiderivative, and I'm going to write this as 125 over 2 because I'm not going to use a calculator to do any of this. And I have 5/8 times, all right, we'll have 64 minus y squared to the 3/2 times 2/3, and we're going to evaluate that from -8 to 0. So let's go ahead, the 2's can reduce out, and we'll get 625 over 8 times 3. I'm just going to leave it like that, and you'll see why in a moment. 64 minus 0 will be 64 to the 3/2 minus, when we plug in -8, we'll get 0. Now we just need to do the arithmetic and simplify it. So I'm going to write this as 5 to the 4th over 8 times 3. And then 64 square root will be 8. So this will be 8 cubed. Now, if I can reduce the 2, so 8 goes into 8, and then the cube. So now I have 8 squared. I want to rewrite that. 8 squared is the same as 4 times 2 quantity squared, and 4 is the same as 2 squared. 2 squared to the squared will be 2 to the 4th, and then we'll have one more 2 squared, all divided by 3. Why am I doing this? Because this is nice and convenient. 5 times 2 raised to the 4th, 10 to the 4th is 10,000. So this will give us 40,000 divided by 3, and we have pounds. And that's it? Yeah, that's it. It's a little challenging, I know. Let's go ahead and we'll see about trying to understand it a bit more with this next problem. So when we're doing this, we have the vertical end of a tank containing water with the density 62.5 pounds per cubic foot shown, and then we're finding the force of the water on one end of the tank. So we're going to, first of all, this is actually the height. We're going to look at one slice, have a delta y. We need to decide where we want to put the axes. What I'm going to do is I'm going to show you a couple different ways to do it. Let's first start off, and we're going to rewrite this graph. Go ahead and do so. All right, I paused it so I could draw those with straight lines. Now, where are we going to put the axes on this one? We're going to set it right here. We'll do it once here, and then we'll do another one in another spot. And we'll have here, that will be 0, 0. Now, typically we have x comma y, but we need to do this right x minus the left x. So instead of doing that, normally, let's go ahead and switch the coordinates of the point. We're going to write it as yx, and that way we can kind of do our standard slope idea of how it's set up. All right, so this point right here is going to end up being 0, 10, and this will be 0, -4. Now you might ask, why? How do I know it's -4 and +10? It really doesn't matter, as we'll see, but for right now, for convenience sake, that's what I'm going to do. I'm just thinking about cutting this down and saying this part over here is 4, 2, and then the rest of that is 8. So I have 6, 2 and 6, 0. So now let's go ahead and find the slope. So the slope of the left side will end up being 0 minus -4 over 6 minus 0. So that gives us 2/3. And now, since we have this switch, we can go straight to the x value will be 2/3 y, and then the x-intercept will be 4. We're going to apply the exact same thing now on the other side. We'll say the slope on the left side will be 2 minus 10 over 6 minus 0. And that's going to reduce, so you have -8, 6, so -4/3. So on the right side, we will have -4/3 y plus 10, our x-intercept. So now we have our length of our rectangle, this part right here, okay, will end up being the x on the right minus x of the left. So -4/3 y plus 10 minus, our parentheses matter, so we'll say 2/3 y minus 4. Simplify that, we get -6/3, so -2y, and then 10 plus 4 is 14. All right, let's go ahead. We're not done with the problem, but let's go ahead and say what would happen if we set this up in a different place. So go ahead and redraw it. So this time we're going to move the axes to be on this spot. So we'll have 0, comma, we'll have 0, 0 here. And if we're taking that same setup, picture is not drawn to scale, this will be 0, 8, and this will be 0, -6. And then up here we'll have 6, -2, and then this will be 6, 0. Again, we're going to use that same yx for writing our point. So now go ahead and do this, hit pause, do this, find the x left, x right, I'll do it, and then we can compare our answers. All right, so there it is. Exact same thing. We should expect to get the exact same length because it really doesn't matter. The length isn't changing, just our axis is changing. And as the axis changes, the right minus left still has the exact same value. So let's go ahead and go to the back side and we'll see what's the easiest way to go about doing this. All right, so let's start with another picture. We have, again, delta y. What is the net takeaway of doing that last one two different ways? We did it using two different sets of axes. It doesn't matter where we put it. The only thing we really need is we need the length and we need the y value because it's a linear relationship. So we have y equals 0, we have y equals 6. This is 14 and this is 2. So our point, what we're going to do is write it as y comma the length. If we do that, we have points 0 comma 14 and then 6 comma 2. This is so nice. All we need to do now is write the slope, 2 minus 14 over 6 minus 0. We get -12 over 6, which gives us our -2. So our length equals -2y plus 14. And that's it. So instead of doing all that other work, all we have to really do is realize this is a linear relationship. We're going to find that depth of the water, and then with that depth, we find the length of, so we're going with that y value with the length of each piece at a specific depth. And where's the depth starting? So in our picture, it's still going to be starting at this point here, and it's going down. And so at the top, we're going to end up having a 0, and at the bottom, it'll be 6. Instead of doing our summation, let's go straight to our integral this time. We'll say the integral from 0 to 6 of 62.5 times what? So if we're going 6 minus y. At the top, when it's y equals 6, then that's where it's 0. And at the bottom, when y equals 0, then we have a depth of 6. And this is going to be our force per area. And now we're going to multiply it by the area. And the area will be our length. So it'll be negative 2y plus 14 times dy. And dy being our delta y when it goes to 0. And now we just need to go through the steps and integrate this. Let's go ahead and pull out, I'm not going to use a calculator again, so I have 125 over 2. The integral from 0 to 6 of, multiply all it out, 14 times 6 is 84, minus, we'll get 26y plus 2y squared, and then dy. Make sure that looks like it. So now we have 125 over 2, and then 84y minus 13y squared plus 2/3 y cubed. And we just have to plug everything in. 125 over 2 times 84 times 6 minus 13 times 6 squared plus 2/3 times 6 cubed. Minus, we plug in 0, we get 0. Now, notice the 6's here. 84 is just 6 times the 14. That's how we got it in the first place. So I'm going to go ahead and factor out a 6 squared. So then I have 14 minus 13 plus 2/3 of 6. So we get 125 times 18 times 1 plus 4, which is 5. And then go ahead and multiply all that out. We get 11,250 pounds. And that's it. So now let's take a look and apply our integrals to area. Now you've all looked at probability stuff before, and we're going to look at it now in light of integrals. So f of x, our normal probability density function for a population with mean mu and standard deviation of sigma, is 1 divided by sigma, that's just a lowercase s in Greece, or Greek, times e to the negative quantity x minus the mean, mu, squared, divided by 2 times the standard deviation squared. F of x is greater than or equal to 0 for all x. Here's the curve of it. The area underneath this curve from negative infinity to infinity of f of x dx is just 1. This is called a normal curve, you know, or yes, it's a bell curve. All right, if we're going to go within 1 standard deviation, that would be, yeah, it's a lovely line. Do you remember those numbers? 0.68. It's approximately 68%, or the probability is 0.68. If we go 2 standard deviations, That'd be all of the area in between those two. That gives us 0.95. And then if we go 3 standard deviations, look at that. That's basically everything. So it makes sense that it's 0.997. Let's go ahead and mark that. This would be right here. This is mu. Actually, I'm going to go back to the blue. This is mu minus 1 sigma, mu minus 2 sigmas, mu minus 3 sigmas. And similar on the other side. Mu plus sigma, mu plus 2 sigmas, mu plus 3 sigmas. All right, let's apply it to a problem. Using the data for the class of 2019, the mean GPA is 3.6 with a standard deviation of 0.6. What proportion of the students in MV's class of 2019 have a GPA of these following ones? Let's go ahead and draw a quick sketch. This value right there is our mean, 3.6. So how much is less than 3.6? Well, that's exactly half because of symmetry. If we started to mark, we could mark down 3 each standard deviation, 2.4, 1.8. So when we're saying less than 2, we're going to say something around this area here. So we should expect it to be quite small. We can also go the 4.2 and etc. We won't need any more than this. So let's go ahead and write the integral. This is going to be the integral from, now how do we decide? We know what we're going to is 2. We could write negative infinity, but really for all intents and purposes we just need to be far away from the mean to say, yeah, that's good enough, because stats isn't such a precise thing. It's more of a touchy-feely math and lab science. So I'm just going to use, if it's 5 standard deviations away, so if I say 3.6 minus 5 times a standard deviation, I get 0.6. That's what I'm going to use here. I could just use 0 as well. You can go ahead and try it out. And let's write this a few times to see if we can get it down. 1.06, 1 over 1.6, our standard deviation, times the square root of 2 pi. Sorry, that should say e, let me just get rid of that, e to the negative x minus 3.6, which is our mean, quantity squared, divided by our 2 times our standard deviation of 0.6 squared. And then dx. Now we just need to type this in on your calculator. I have an 84 set up. I've already typed in the equation here, and you can kind of see the negative of the quantity x minus 3.6 squared divided by 2 times 0.6 squared, and then you can see the coefficient part, 1 over 0.6 square root of 2 pi. So if we go back to the home screen, we'll go math 9, we're going to go 0.6, and then up to 2, and then we need to go put our y1, so I'm just going to go second, and then the trace button, and we can get our y1 that way, and then x, hit enter, and it's quite a small number as we expected. Now for this kind of stuff we can just write 0 equals, because it's not such a precise thing. 0.0038. Typically we're just going to write 3, but in this particular one, since it's so small, I'm writing 4, but we'll just write 3 in general. All right, between 3.5 and 4, we're just going to set it up. So 3.5 to 4 of the exact same thing. Try to think about it while you're writing. 1 over the standard deviation, square root of 2 pi. E to the negative x minus the mean quantity squared divided by 2 standard deviation squared. And then we have our dx. So go back to our calculator, bring it back, and then just change our numbers. Let's see, my delete. We're going from 3.5 up to 4. Hit enter, and we get that number. So we'll get is approximately equal to 0.314. Let's go ahead and show that over here. So 3.5 would be to 4 would be something like that section. So we're giving that area is approximately 0.314. And the very last one, do you know what it is? You may not know immediately, but as soon as we start to write this integral, let's go ahead and write it one more time. We're going from 3.5 to 3.5, and at that point I know you know, yes, it's going to be 0 because it's just 1 point. But if you think about it in terms of the context of the problem as well, you would say, what's the probability of exactly one number occurring from an infinite number of possibilities? Yes, that's just 0. So take a look at all of this. If you have any questions, bring them in tomorrow. There's some meaty things going on, some difficult stuff there. Look it over and be ready to ask some questions, and we can go over that again. And that's it.